Welcome back to our session on effective network inference using information theory. In our previous short video, we looked at using the pairwise transfer entropy for effective network inference, and we identified the issue that it does not address redundancies or synergies between the sources. In this short video, we're going to look at building a more advanced algorithm to account for that issue. So the key question then is, what could we do to address redundancy and synergy here? As I've said a few times during this session now, if you've been paying attention in the previous lectures, you've probably already worked it out. We can remember that conditional transfer entropy addresses redundancies and synergies very well in all of these examples. For example, in our common driver scenario and in our pathway scenario, if we're looking at the effects of Z or Y on X and conditioning on the other one, then we'll typically get the right answers here. If we look at the effect of Y on X and condition on Z, we won't see an effect here. And same for this example. If we look at the effect of Y on X and condition on Z, we won't see an influence from Y. However, if we look from Z to X and condition on Y, in both cases we'll still see the effect of Z typically. Similarly, in our example of synergy, if we don't see a pairwise effect from Y or Z on X, but if there's a synergistic effect, the conditional transfer entropy from both of them conditioned on the other will then show us an effect. So conditional transfer entropy does what we want in these scenarios. It addresses both redundancy and synergy. But we still have a question. What should we condition on? We could condition on all other variables. That's kind of the first idea that we might have. But if we do that, we can undersample very easily. We can easily imagine here having a system of maybe 100 variables. Maybe we have 100 beamformed MEG sources and we want to analyze the network between them. It's very, very difficult to sample a state space of 100 variables very well. So trying to condition on all other 98 variables there when you're looking at the relationship between two of them is just not really possible under realistic circumstances. On the other hand, we could eliminate too many links from our model. In this situation on the right here, where both Y and Z are driving X, it may be the case that they're largely carrying the same information to X, okay? And that we may see that situation in many of the networks we look at in nature, particularly if Y and Z have a similar set of parents. They could very well be conveying very similar information to X. So if we look at the conditional information from Y to X given Z, or vice versa, the conditioning could actually eliminate a lot of the information that's really being carried here. So we might actually eliminate both of those links from our model, and we don't really want to do that. So we need to solve this question. What should we condition on? To consider that question, what I first want to do is take a step back and take a bit more of a high level view. Let's have a look at this slide that we first came across in our lecture on information transfer before. So here we were talking about modeling the information processing in X, and in particular, we were talking about creating an information regression between our information storage and our information transfer in modeling the information processing in our target variable X. On this slide, I'm just giving you the mathematics for two sources. You can see the general case in some of those papers below. So here, what we talked about was how we could do this regression in multiple ways if we had multiple sources. So here we've got two sources to X, and we could do a regression where we first consider the transfer from source Y and then consider the transfer from source Z conditional on Y. Or the other way around, we could look at the pairwise transfer from source Z first, and then the pairwise transfer from source Y given Z. What's important though is that whichever way we do the regression between these two, they are consistent with the answer provided by looking at the sources as a collective. Okay? Looking at that, we can see that that's the real goal here in our effective network inference. Our real goal is to infer this parent set of y and z together as the parents for x. It doesn't matter so much which route we take in our regression, in modeling the information processing, whether we look at y first and then z, or z first and then y. Our real goal is to infer this parent set, which we get with our collective information transfer here. Okay. What we need to bear in mind is that inferring that whole parent set at once, though, is combinatorially difficult. We may have a data set with tens or even hundreds of candidate parents. There could be a factorial number of possible parent sets that we might want to evaluate here. So trying to infer that whole parent set in one go is a very difficult thing to do. So instead, the suggestion is to take a greedy approach here, or an iterative approach, to infer the parent set one by one. And we can think about doing this as exploring the different regression routes that we looked at on our previous slide. Let's look at that in more detail here. What we could do in an algorithm is to start with an empty parent set for x. From that, we could then evaluate the transfer entropy from each of our candidate sources to that target, conditioning on the existing parent set. So in this step here, we're simply talking about measuring a transfer entropy from source y to x and source z to x, and there's no one else to condition on at the moment because there's no one in our empty parent set P yet. Once we've done that, once we've evaluated the transfer entropy from each of these candidates, we can then take the one with the maximum conditional transfer entropy, condition on the existing set P. We can take the one with the maximum measure if the p-value of that measure is statistically significant. So here what we've shown in the diagram is that we selected y as having the largest transfer entropy out of our sources, and we're going to add it to our parent set P if it's statistically significant. Let's assume that it is for the moment, and then if it is, we go back and we evaluate trying to add a new parent to the parent set. If it wasn't significant, we should terminate straight away. If it was significant, we can go and evaluate other candidate sources here, conditioning now on P, which includes y as our selected parent. We take the one with the maximum conditional transfer entropy. Here we've taken z. I haven't shown you the other candidates here, if there were more nodes in the network, and we add it to our parent set if its p-value is statistically significant. Okay. Once we reach a point where the candidate sources are not adding any more statistically significant information, then we terminate the algorithm right there. In our next short video, I'm going to add some subtleties to how we can do that and go into a bit more depth on some of these steps.